Okay. Yeah. Hello, everyone. Thank you for coming today. So I'm very happy to have Bharath here today. So he's a professor of statistics at Penn State University. He's done a lot of fundamental work on kernels, reproducing kernel Hilbert spaces, Hilbert space embeddings and probability measures, a lot of stuff. He's, a co-author on the very famous monograph of, connections between Gaussian processes and kernels, which I guess will be published as a book soon. He also has very strong connections to UCSD. So he did his PhD here, completed in 2010 in ECE. And more recently, he's gotten into topics like optimal transport, gradient flows, Gromov-Wasserstein geometry. And today he's going to tell us about those topics and their connections to reproducing kernels. So Bharath, please take it away.
Thanks a lot, Rahul. Thanks for the nice introduction and thanks for the invitation. So this visit in some sense happened because of the recent collaboration that we started with Rahul on some interesting connections between harmonic analysis and neural nets. Okay, so very nice to be back to San Diego, and this is the first time I'm coming back after I graduated in 2010. So nice to be back here. So this is based on a couple of recent works that I have done with collaborators. But before I dive into the work, which probably could be like 30 minutes into the talk, because I don't want to assume anything about the background of the attendees. So it's going to be like I need to build up certain background before we actually get into what the work is. Okay, so the topic is going to be about how gradient flows have permeated into machine learning and statistics. And then we'll look at this notion of course, these gradient flows are the two key ingredients in gradient flows is like what is the energy function that you're trying to minimize and what is the corresponding geometry with respect to which you're doing this optimization. And how one can talk about regularizing or deregularizing these two objects in achieving certain goals, right? So that's going to be the theme of the talk. So as you see, there are many problems in statistics and machine learning that can be formulated as like minimization problems of certain probability functionals over the space of probabilities. And I have listed out many applications here. I'll just explain like few applications just to convince you of where these problems come into picture. And then we'll see how this problem can be solved as like gradient flows on the space of probabilities. Okay, so to start with, so we are familiar with Bayesian inference, which gives you the posteriors. And many times these posteriors are intractable unless you use like a conjugate prior. The posterior becomes intractable, and therefore questions could be, now if I need to play with the posterior, I need to have some samples from the posterior so that I can kind of whatever objects that I want to compute from the posterior, I can approximate it based on the samples from the posterior. So the sampling is like a very natural question that comes into picture, which is now if I give you a probability density pi, so the pi that you see throughout the talk is going to be the target, which we want to in some sense approximate. So given this probability measure pi on RD, so we want to generate samples from it. However, this target measure may be known only up to a normalization constant. Okay. I mean, if you know the full normalization constant, there are methods, very classical methods. If you don't know the normalization constants, of course, you can still use Langevin or Markov-Chain Monte Carlo. So there are algorithms. It's not like there are no algorithms. There are algorithms, but the sampling question is basically to draw samples from a distribution where we know only up to a normalization constant. Right. So the other way to solve this problem is through this notion of variational inference, where the idea is, okay, so you have this intractable posterior, this distribution pi, but I want to approximate it or by a tractable family of distributions, which I denote by Q. The tractable family could be a parametric family, okay, maybe a mixture of Gaussians or vanilla of Gaussians parameterized by mean and the variance. And therefore, the variational inference problem is I take like certain type of a divergence functional on the space of probabilities, and I look at the divergence between my distribution in the family to the target distribution, and we want to find that element in the approximating family that minimizes this thing. So So here we can, usually this divergence is chosen to be the KL divergence, but choice is ours, right? So, but essentially we can see the variational inference problem is nothing but doing an optimization on the space of measures. When I introduce a sampling problem, we didn't see how the sampling problem is also an optimization on the space of measures. We'll come back to that question later, right? But we'll keep in mind that the sampling problem that I introduced is also an optimization on the space of measures. The variation inference problem that I introduced is also an optimization on the space of measures. The other application where similar problem comes into being is in generative modeling, where here the problem is we want to generate samples from a distribution pi, but I don't know anything about the distribution. I only have access to some samples from the distribution. So the distribution pi, the target distribution is known only through some samples, and I want to generate a new set of samples from this distribution, right? So in that sense, this is different from the sampling problem. And in this case, one of the popular ways to do this is through generative adversarial networks. Now there are other methods like diffusion process and so on and so forth. So in this case, as you can see, we can use certain energy functional. This energy functional here, I'm just showing the energy functional to be the IPM, the integral probability metric, which looks at the distance between two measures, right? So think of F as a class of test functions or your discriminators. And once we have the distance between the measures, I want to basically find a measure in my class which basically minimizes this distance. Okay, so D is a discriminator class. Many choices have been used in the literature, and G is a generator class. Usually this is like a parametric family, or it could be like a base distribution nu that is pushed forward through maybe a neural network. Okay. And then in neural network training, for example, in a two-layer neural network training, so this is your two-layer neural network. In the mean field limit, this quantity basically converges to this integral over the measure mu. So now we can think of the neural network training rather than doing in the space of parameters. Now we can think of optimizing on the space of measures. And that is again an optimization problem, the one that I have introduced previously. Right. So this is another problem called as the style transfer problem, where if you have like a content image and multiple style images, so we want to basically transfer the style from given those four images, we want to kind of transfer the style from those images into the content image, and we can write this as like a barycenter problem over the space of measures. Okay, so there are a variety of problems in machine learning and statistics that can be posed as optimization problem on the space of measures. Before we get into how do we solve these problems, so we'll look into the Euclidean version of this problem. So let's say I give you a cost function f, and you want to find the minimum or the minimizer of this function. Okay, so one can use gradient descent, which is what I have mentioned here, right? So the continuous version of this gradient descent is the gradient flow. The gradient flow is defined through this ODE, where it says, if you think of xt as the position of a particle at time t, now the time derivative of x of t is going to be the velocity of that particle, and we say the velocity of the particle is now defined through some vector field v. Okay, the velocity of the particle is defined through this vector field v, and this vector field v at the location xt defines the velocity of the particle at that point. Okay, so this is the ODE, which is governing the dynamics of the particle. And if I choose the vector field to be the gradient of the function that I want to minimize, then you call this as the Euclidean gradient flow of the function f. Okay, and the discretization of this ODE gives you the gradient descent, where gamma is the step size. And here we can show that if you basically choose the vector field to be the gradient of f, then clearly the function f, it decreases along the flow, because the time derivative of f of xt is going to be less than or equal to 0 along the flow. Okay, so you choose a direction which is along the negative of the gradient of f. Okay, so now these are very classical results in terms of, so we know that if the function is like strongly convex, then it has like one the unique global minimum, and then you have the convergence. So a weaker condition is this gradient dominant condition, or the Polyak-Lazarevich inequality, where the gradient is dominated by an object like this, and this is satisfied by strongly convex functions and so on and so forth. Under this condition, one can show that the gradient flow actually converges to the so f star is the minimum value attained at the minimizer. So we can show that the gradient flow actually converges to the target at an exponential rate. Okay. So Euclidean, and therefore, if you assume a little bit more, which is like if you also assume that uh, the gradient of f is basically Lipschitz, then you can show that the Euclidean gradient descent converges exponentially fast. But without that assumption, you can show that the gradient flow converges exponentially fast. Okay, so this is for the Euclidean setting. Now the problem that we want to solve is I want to minimize some energy functional over the space of measures. So therefore, like in the Euclidean setting, I could solve this problem as a gradient flow. Okay, so the gradient flow is basically this PDE, because these measures are defined on, let's say, RD. So these measures now mu t has basically two coordinates, like the spatial coordinate and also the time coordinate. So I'm taking the derivative with respect to the time coordinate. So this is exactly like what we saw in the Euclidean gradient flow setting. It's just that now I have to define, how do you define a gradient on the space of measures? Okay, so, and I put a dot there just to show that this gradient can be defined depending on what sort of metric that you consider on the space of measures. Okay. So therefore, the two ingredients that play a role in this optimization is we need to, unlike in the case of the Euclidean setting, so here because where there is an intrinsic geometry in the case of the Euclidean space, here we need to define what is the geometry with respect to which we need to define the gradient and what is the energy functional that we are working with. And this PDE, we call it as, depending on what geometry I choose, I say it is like it's that geometry. So it's a dot gradient flow of the energy functional. Okay. Okay, so many probability functionals have been used in practice. So I'm just going to give you a list of combinations of geometry and the energy functionals that have been used for a variety of applications. Okay. So here, so F divergences, particularly like the KL divergence and chi-square divergence, has been used as energy functionals. The integral probability metrics have been used, particularly when your the class of test functions is a unit ball in the RKHS, or like a unit Lipschitz ball, or a unit Stein RKHS ball. The popular dissipation geometries are the Wasserstein 2 distance. So this is the most popular one. Classically, when these PDs are studied, so we'll see the classical connection to how 2 Wasserstein distance actually plays a role. So the popular geometries, at least in the applied mathematics literature, are like 2 Wasserstein, Hellinger, and then Wasserstein-Fischer-Rao. But then in statistics and machine learning, even in the applied mathematics community, there are like other geometries that have been explored in the literature, like the Gromov-Wasserstein, MMD, the Stein distance, so on and so forth. So depending on the geometry and the energy functional, you end up in different gradient flows, you get different PDEs, and then depending on like what sort of applications we want to deal with. So here are some examples of these gradient flows. So for the sampling algorithm, by the way, if you have any questions along the way, feel free to interrupt me. For the sampling algorithm, the popular algorithm is the Langevin. Okay, and there are many variants of this Langevin, but all of them basically deal with the energy function being the KL divergence and the geometry being the 2 Wasserstein, right? And the rest of the works, as you see, like by varying different geometries and the energy functions, you get like different algorithms to do sampling. And the key to note is all of them have either some variation of KL as the objective and some variation of 2 Wasserstein distance as the geometry to solve the sampling problems. And in this work, I will be talking about this paper, which got published last year in the Foundations of Computational Mathematics, where we work with some geometry being the geometry is like an approximation to the two Wasserstein distance, and the energy function is the KL divergence. Okay. So we'll see how that is related to the classical work, this one. And in generative modeling, again, the popular geometry is the two Wasserstein distance, and then there are different energy functions that have been used in the literature. So in this talk, I will be looking at this paper which got published, actually this is in 25, this got published last year in JMLR. So where we look at the two Wasserstein geometry, and then we look at the energy function being some version of an approximation to the chi-square. Okay, so we'll see we'll see the connections of where this regularization is going to play a role. So in one work, the regularization plays a role in the geometry. In the other case, the regularization plays a role in the energy. Okay. And then the other line of work is in variational inference. So for variational inference, like there are works, again, all of them deal with the KL as the energy functional. And then you use two Wasserstein as a geometry, but then there is an approximating family that you need to consider for the variational inference. And the approximation family is the simplest one is Gaussians, but then you can also work with mixture of Gaussians. But you can also change the geometry from the Wasserstein geometry to the Wasserstein-Fischer-Rao geometry, and then work with mixture of Gaussians. So this is a recent work which is yet to be posted on archive, but I won't be talking about this work. Okay. Okay, so before we move on, I'll start with a quick primer on Wasserstein gradient flow. Okay. Okay, so the problem here is, I mean, let's consider this picture. So we can consider X to be a volume of sand that we need to basically dig, and it has to be transported to construct this factory. Okay. Of course, which means the amount that I'm digging is exactly the thing that I'm going to use to build this factory. So which means the amount of mass that I'm transferring is conserved. Okay, there is no addition or the destruction of mass that's happening. The mass is conserved in this transport. And there is a cost involved in moving the mass from a location X from which I'm digging, and I'm going to transfer that amount of sand in constructing this building at a point Y. Okay, so there is a certain amount of cost that is involved in this transfer, and we basically look at the average cost it takes to do this transfer, and we say among all possible ways of transferring this material, what is the one that gives me the least average cost? Okay, so that is what we have mentioned here. So T is the map that is basically push forwarding the measure mu to a measure nu. Okay, among all such possible transport maps, what is the map that has the smallest cost of transfer? Okay, and this was a problem that was posed by Munch in 1781. And then, I mean, it's a nice problem, but it turns out when you ask about the question about the existence of such a T, and even if it exists, like whether it has a unique minimizer. So here is an example where supposedly I'm transferring a Dirac mass to, let's say my initial measure mu is just 1 Dirac, whereas the measure nu is a mixture of 2 Diracs. As you can see, there is no transport map for this problem, because the way we pose the problem is the transport map has to be like 1-to-1. Okay, so there is no solution to this problem. So therefore, there have been relaxations of this problem by Kontrovich, and it's a very big area in mathematics with connections to many areas in mathematics. Okay, so while we don't get into, yes. Oh, so the way we are posing this, because every x is getting transported to only one corresponding y.
Oh.
Like that's how the T of x gives me like only one element in the y space. So the counter-wedge relaxation basically takes that into account and writes a dual version of this. And then the famous theorem is by Brenier, which says like when do these two formulations, the Munch formulation and the counter-wedge formulations match? And when your cost function is like the Euclidean cost, then the Brenner's theorem says that such a transport map, the optimal transport map exists, it is unique, and it is given by the gradient of a convex function. Okay, so the optimal transport map has the structure that it is the gradient of a convex function.
What's the reason you cannot split the atom again?
Oh, because by definition, I'm saying the cost is looking at from x to y. Right.
You cannot map it to a probability distribution.
Correct. The way the Munch problem is posed. Correct. Okay. So so now if this the input measure, the mu, if this is absolutely continuous with respect to the Lebesgue measure, then Brenner's theorem says such an optimal transport map exists, it's unique, and it's the gradient of a convex function.
Just a question. So you said that P star is the potential conjugate.
Yeah. So I should I think I had like a little bit an additional statement that I had, but I removed for this one. I didn't remove this. Yeah, ignore that. Just a gradient of a convex function. And this phi actually are the counter-wedge potentials which come in the dual form, but I didn't mention that. Yeah. Okay. So now we consider the Wasserstein space, and the Wasserstein space is now, rather than considering this optimization over the space of all measures, I just consider only P2, which is a space of measures which have finite second moment. Okay. And then I induce that space with W2, where W2 is defined in this way, which is the two Wasserstein distance. Okay, here again, I'm using only the Munch formulation to do this, and I'm not getting into the contour, which not needed for this talk. So we know that if mu is absolutely continuous with respect to Lebesgue, then T star exists, and therefore I use that to define the two Wasserstein distance on the space of measures. So now a Wasserstein space is the P2 endowed with W2. So that's the Wasserstein space with which we'll work. And here is the alternative interpretation of W2. This is this famous result due to Benjamin-Brenier, where this gives you the pseudo-Riemannian interpretation of this Wasserstein space, right? So what this basically is saying, we can interpret W2 as, suppose, so it basically says if I have a curve starting from mu to nu, so there are many possible curves that connect from mu to nu. Of all the curves that connect, all those curves have to satisfy this equation. This is the law of conservation of mass, which is called as the continuity equation. Okay, so you have many curves that go from mu to, so in this case pi, the pi is the target, so I change mu to pi. So we need to move from mu to pi, and there are many curves that transport mu to pi, okay, while conserving this mass. And here this Vt is the vector field that is driving this movement of the mass, okay. And this equation is saying among all such curves, you pick the curve that has the smallest length, okay. So that is the interpretation for this W2. And here, because now you are talking about a pseudo-Riemannian structure, so you can look at the tangent space, and the length, the vector field Vt that you are considering is now measured as the elements on the tangent space. Okay, so that is how you measure the length of the curve. So W2 is looking at the shortest path from mu to pi. Okay.
There's also unique for this pattern.
Yes, that is this.
Yeah, okay.
So in this case, if in W2, the geodesics exist, and that is the unique one. And that is defined through this optimal transport map T star. Okay, so now having this machinery, we can define the Wasserstein gradient now as using the usual directional derivatives, but now the directional derivatives, we are first doing this transformation in the tangent space because T is now an element in the tangent space. We do like an epsilon perturbation along the direction T in the tangent space. And then once which means, so if I have this manifold and here if I have this curve, so this is my tangent space. And here we have certain T, we perturb along the direction T. Okay, and then we use the exponential map to pull it back onto the curve. Okay, and that is this object. And then I evaluate what is the value of my functional at that point. Okay, and the Wasserstein gradient is defined as, okay, if there exists an element in the tangent space such that it satisfies this property for all T, okay, then you say this object is the Wasserstein gradient of the functional f. Okay, and it can be shown that this Wasserstein gradient is precisely has a precise form like this, which is defined in terms of the first variation of the function. Okay, so therefore, when I say the Wasserstein gradient flow of the functional f, so we already mentioned the gradient flow is going to be dou t mu t is equal to negative gradient of f of mu t. And here this gradient dot is going to be the Wasserstein gradient. It's going to be gradient W2 because that's the geometry that we are working with. Okay. And given the Wasserstein gradient is defined as this, so directly using this in the gradient flow equation gives us this PDE. Okay. So these are all very classical, right? So this is all very well understood, very classical. So now let us see how this ties back to the sampling problem, right? Okay, again, just to revisit, the sampling problem is you have a target density which is proportional to, let's say, e to the negative v. So v is the potential function. So which means I only know this target up to a normalization and we want to generate samples from it. The popular algorithm for sampling is this Langevin Monte Carlo. Okay, so this is again very classical dynamics, right? So essentially, you can see that this is just a gradient descent, but with an additive Gaussian noise error. Okay, so this is a stochastic algorithm, which when it converges, the particles have a distribution which matches with phi. Okay, so this is the discretization. The algorithm that I showed here is the discretization of the Langevin diffusion, which is this stochastic PDE. Okay, and this stochastic PDE is well understood to be the Fokker-Planck equation of the Langevin diffusion. Okay, so this is the Langevin diffusion. Okay, and this is the Fokker-Planck equation of this SDE. The seminal work, in fact, all this connection between PDEs and gradient flows in some sense actually started from this work by JKO, Jordan, Kendall-Error, and Otto, where they provided a variational form for this PDE, the Langevin diffusion PDE. And therefore, that begged the question saying what other PDEs can be written in terms of this variational form, so on and so forth. So they showed that this Fokker-Planck equation can exactly be written as the gradient flow of the KL divergence with respect to W2. So the Wasserstein gradient flow of KL is exactly the Fokker-Planck equation. Okay, so now this is how the connection to sampling comes up, because sampling problem can be solved using Langevin Monte Carlo, which is a discretization of Langevin diffusion, which has a certain Fokker-Planck equation, and the Fokker-Planck equation has a variational form. Therefore, it is the Wasserstein gradient flow of KL. Okay, so therefore now let's treat sampling problem in the continuous setting as the Wasserstein gradient flow of KL. Okay. So this is the problem that we want to solve. And if I solve this problem as a Wasserstein gradient flow, I exactly get back my Langevin dynamics, and then I can discretize the dynamics and I get a sampler. Okay. So here, if you see, if I take this scale, now because we said pi is proportional to e to the negative v, just doing calculations, you can show that there are these two terms. One term is linear in mu, the other term is the entropy term related to mu. Okay, plus some additional constant which is immaterial, does not depend on mu. So now if I want to construct a sampler, I have to now look at the discretizations of the PDE. I have to look at the discretization of the Fokker-Planck equation. Okay. So many discretizations are possible. The classical discretization or the Langevin Monte Carlo that we see is precisely called as the forward flow discretization, where in the case of forward flow, what we do is we apply a gradient descent as a way to discretize the first term. And for the second term, you don't actually discretize this. You basically solve this, you solve it as a PDE, and that PDE basically, because I'm minimizing this term with respect to the Wasserstein, the solution to the problem is it becomes a heat equation. And the solution to the heat equation is Gaussian, and that is how we end up getting the Gaussian errors here. Okay. So this Langevin diffusion that we see is the forward flow discretization of the Fokker-Planck equation. But then the problem is the forward flow discretization is shown to be biased, which means the stationary distribution of that SDE is not the target. Okay, so there are other unbiased time discretizations called as you can apply like both a forward discretization and forward discretization here, or you can do forward, backward, forward, or like you can do like backward. So what do I mean by is a forward discretization is simply a gradient descent. Okay, so this is precisely a gradient descent update. Whereas, so as you can see, this is the gradient descent update. Okay, so this is my functional, the KL functional. I'm looking at the gradient of that, and then which is so you get exactly the gradient descent type of updates in the forward. The forward is exactly that. And in the case of backward, what you have is it's a proximal method. Okay, so you have your energy functional, plus you also take into account the geometric information. So you're saying, I want to minimize the functional, but at the same time, I don't want to be too far away from whatever my target is with respect to the underlying geometry W2. And then you can swap the forward and backward. The point being, all these discretizations, even though they give you theoretically the correct stationary distribution, the particle discretization is very difficult. So this is only the time discretization, and from here, okay, here you have a particle discretization. But in the particle discretization, if you see, this discretization now depends on mu k and pi. Okay, so you need, and if I have only particles from these measures, I cannot use like a simple Dirac approximation to these measures. One need to do like a KDE to discretize, to kind of approximate these densities. Okay, so here is where the recent work that happened kind of plays a role, called as these interacting particle systems, where this work kind of considers is, okay, so this is the PDE that I want to discretize, right? So this is the Wasserstein gradient flow of KL. So this work says, okay, this is difficult to discretize, but what we say is, we take this Wasserstein gradient, we'll smooth it through some integral operator. Okay, when you smooth it through integral operator, we will see that this becomes very easy to discretize. Just a forward discretization is sufficient, which means your updates, the particle updates, are just going to be like a simple gradient descent. Okay. So here I have written the integral operator, where the capital K is the reproducing kernel. So that's how kind of kernels came into picture for this topic. Right. So now if you look at what happens to the smoothed version of this gradient of log mu t by pi, here you can basically use integration by parts, and then you can see that the entire thing can be written as an integral with respect to this measure mu t. Okay, so now what is the idea? The idea is, let's say I start with some random set of particles, then this object can be approximated using an empirical approximation, because this is, I'm just doing the integral with respect to d mu t, and even though I know pi only up to normalization, because the algorithm depends only on grad log pi, so the normalization does not play a role here. So therefore, we should be able to discretize this and implement this, and you will have a sampler by doing this method. Okay, and this is what is called in the literature as SVGD. It's called as the Stein variational gradient descent. Okay, so the forward discretization of this approximate PDE, we still don't know whether this is a gradient flow. Okay, because I don't know, because I have changed the gradient. The actual gradient is this, but I changed the gradient by smoothing. So I don't know whether this PDE enjoys the gradient flow structure. I don't know whether there is a corresponding geometry and energy functional that gives me this PDE. Then I can call it as a flow. Okay. But it has been shown that this actually enjoys a gradient flow structure. So the cost function, the energy function remains Kullback-Leibler, but the geometry, because of the smoothing, geometry is no more the Wasserstein geometry. It is called as the Stein geometry, and it is defined in this way. So if you remember, when we define W2, the W2 is looking at among all possible curves that satisfy the continuity equation. I want to get that curve which has the shortest path. Okay, and the shortest path is measured through the L2 norm of these vector fields which are lying on the tangent space. But now that norm is changed from the L2 norm to an RKHS norm. Okay. Now if you use this as the distance, then with respect to this geometry, you can show that whatever this PDE is a gradient flow. Okay, so you can call this as like the Stein gradient flow of KL. It's not the Wasserstein gradient flow, it's a Stein gradient flow because I'm just calling this distance as the Stein distance. Okay.
Basically, I mean, you have this PDE that's transforming these probability measures, and you're just embedding these measures into an RKHS.
No, I'm not. I'm not embedding the measures in the RKHS.
Okay.
So all I'm saying is you. So let's say you have this curve, some curve like this, and this curve is living in the. Of course, this curve is not living in a vector space. Okay, I'm not now. So now let's say I take at this point, I'm looking at a tangent space. Now on the tangent space, you're going to put some metric tensor. In the previous one, that is defined through L2. Now I'm defining it through the RKHS.
Oh.
But the measures themselves are not embedded into the RKHS. So the transport is happening because I need to define the vector field which is going to now push the measures. And how that vector field is defined and how the similarity is defined is through, in the previous case, it is defined through L2, now it is defined through RKHS.
So in the continuity equation with the Stein metric over there, the smoothing doesn't apply to the vector field in the
Smoothing doesn't apply, but the only restriction is that VT has to be in the RKHS. Otherwise, this distance is not valid.
So it's implicitly.
It's implicitly that VT is in the RKHS. Yeah. Yeah.
So is this a regularization on the procedure before?
No, that is what I'll. Okay, we can think of it as a regularization of the procedure.
Restricting space.
Correct. You are restricting your tangent space. So now what we'll do is we'll deregularize this problem so that we want to, what I want to discretize is the Wasserstein flow. But so whatever the discretization that I'm getting is not of the Wasserstein flow, but of the Stein flow. But if I want to get a discretization of the Wasserstein flow, is like I need to now deregularize because I have already regularized here. Okay, so if you look at this algorithm, so it's kind of very interesting. Let's say this algorithm is not really a discretization of the Wasserstein flow, but nonetheless, this algorithm is completely implementable. Okay, and this is an interacting particle system because every particle interacts with every other particle in the system, which is not the case with Langevin Monte Carlo. In Langevin Monte Carlo, I just take one particle and I just keep updating. So if I show this algorithm, so if I take only one particle and that one particle is just getting updated every iteration. But in SVGD, I take a collection of particles and a particle, let's say ith particle in k plus 1th iteration depends on every other particle in the ith iteration, in the kth iteration. Okay, so that's and another point to make here is, unlike Langevin Monte Carlo, this is a completely discrete algorithm, sorry, deterministic algorithm. There's no randomness in this algorithm. Okay, so this became pretty popular. And once this algorithm became popular, people want to understand whether this actually enjoys a gradient flow structure, and that's how this work came into being. Yeah.
It's quite expensive to implement. You need like every pair of particles.
Yeah, these like order capital N square if you start with capital N particles. Yeah. I mean, if you call this as expensive, the one I'm going to propose is like N cube.
What's a sort of realistic number of particles?
I think at least for the papers, I mean, I just only worked with like tie examples. But yeah. Okay, so I think probably I'll skip this. So I'll just show one thing because this is something that is that we'll use for the rest of the talk, which is this condition. So this is sort of a smoothness condition that we'll be considering for the rest of the talk. It basically says, if I'm saying the range space of some gamma power of the integral operator, so there is an integral operator which is basically mapping L2 to L2 functions. And if I'm looking at the range space of such a fractional power of such operators, then we should consider them as like an interpolation space between the RKHS and L2. And when this gamma is exactly half, it corresponds to the RKHS itself. Okay, so because we are not making any convolution type of structures assumption on the reproducing kernel, so if I want to impose a certain type of smoothness, the smoothness is now imposed through these interpolation spaces. Okay, so now here is the first line of work which is done jointly with Ihe, Krishna and Jiang Fang and published at FOCM 24. So the question we started with is, okay, so the SVGD gives some sort of discretization of not really the Wasserstein gradient flow, but some approximation or a regularized version of this Wasserstein gradient flow of KL. Now the question is, can we basically get an exact realization of this Wasserstein gradient flow, still keeping this deterministic flavor? Okay. Okay, so to this end, the intuition is basically this. So consider this PDE that I'm showing. In this PDE, suppose I neglect this term, that is precisely the SVGD. So I took the vector field and I smoothed the vector field. Okay, and what we do here is, because multiplying by that, the action of that integral operator is basically regularizing your flow. What we do is, now we kind of deregularize by looking at a regularized operator. Okay, so in this operator, if I choose nu to be 1, okay, I get back the SVGD. If basically nu is close to 0, right? So then you are working with some version of, you are taking this operator. I mean, if nu is exactly 0, I'm basically getting like T inverse times T, but technically T inverse is not defined. So therefore, we had to do the regularization. So you can see T inverse times T is kind of like in approximating an identity operator, and therefore this flow is sort of an approximation to the Wasserstein gradient flow. And this we call it as the deregularized Wasserstein gradient flow of K. Okay. Now we can ask the question whether this flow has a gradient flow structure. So which means we show that this has a gradient flow structure, that you work with the energy functional to be the KL, but the geometry is now the deregularized Stein, so which is defined in this fashion. So previously when we were doing only the Wasserstein flow, this term was not there. You had only the L2 as a way to measure is the metric tensor on your tangent space. Okay, and when we did SVGD, this term was not there. It is only the RKHS norm. So now you look at the mixed norm, and this mixed norm is the one which basically gives you the previous PDE that I showed. So with respect to this geometry, we call it as the deregularized time distance, or you can say the regularized Wasserstein distance. It is this geometry which basically gives, along with the KL functional, with this, with the continuity equation being satisfied, is the gradient flow that I showed here. Okay. So now the particle formulation. So we can still so using this PDE can be discretized, and here is the discrete version of that PDE. Okay, so this discrete version, as you can see, has an additional factor of a gram matrix inverse multiplied by rest of the terms. So the rest of, if I remove this inverse part, then you have only SVGD. If you add this inverse part, you get the regularized SVGD. Okay, but now because of this inverse, the computational complexity is now like order n cube. Okay, okay. So here are some toy simulations that we have, really toy simulations. We are writing the math journal, so we could get away with it, but okay. So the target is mixture of two Gaussians. Okay, and this is the initial distribution from which we draw the samples. And what we are interested in is we want to look at the expectation of some test functions, the expectation with respect to the target measure pi, okay, which I can compute. In this case, the target measure is basically known. And these are different test functions that we considered. So which means I'm looking at the mean, the second moment, and the expectation of this cosine function for the target. Okay, and what we used is the Gaussian kernel. And these to basically kind of convince ourselves that whether the deregularization that we are doing is basically any better than SVGD. So here, as we see that all these charts basically show for these three different test functionals, as the number of particles increases, so first of all, your MSE is reducing. Okay, so which means I'm basically getting closer to the true expectation. And you have three colors which basically saying the regularization parameter. As the regularization parameter becomes smaller and smaller, your flow is getting closer and closer to the Wasserstein flow, the true flow. Okay, when nu is equal to 1, that is the algorithm corresponding to the SVGD. And when nu is becoming smaller and smaller, it is basically approaching the Wasserstein flow. Okay, so you can see that you get a much smaller error with the Wasserstein flow than with the SVGD flow. And here is the result by fixing the number of particles. We fix the number of particles to 200, so it's too small a number in eyes of Misha. So we looked at 200 samples, and then we see, like, as with the number of iterations grow, what happens to the MSE. And again, here, as you see, as the regularization parameter becomes smaller and smaller, like, you have faster convergence. Okay, so maybe I'll directly show some result. So we have, I mean, in the paper, there are results about like both continuous time, discrete time, and also the particle convergence. Okay, so I'm just going to show you only the continuous time convergence, and if you're interested, you can refer to the paper for the other results. Okay, so let's say, let's consider this. So let's say this is the deregularized Wasserstein flow that we are considering. Okay, and we start this PDE with some initializer rho naught, and if the target satisfies this log-Sobolev inequality, so the log-Sobolev inequality is defined in this fashion. This is precisely the gradient dominance condition that I introduced in the case of Euclidean gradient flow. Okay, you need the gradient if the gradient dominant condition holds, then the Euclidean gradient flow converges exponentially fast. Okay, so this is a similar type of a condition because the Fisher information I is precisely the gradient of KL. Okay, so the gradient of KL is dominated by the KL itself. That is the Lox-Sobolev inequality. So under the Lox-Sobolev inequality, we can show that this flow, it actually converges to the target pi. Okay, it converges exponentially fast. So this is the type of result we would get, plus an additional error, and this error basically vanishes with the regularization parameter nu. Okay, you have an additional error because I'm approximating the flow. Okay, so, and if you have a stronger inequality called as a deregularized Stein LSI, so we don't know whether this inequality really holds or not. Okay, so for what sort of measures does this inequality hold? For what sort of pi does this inequality hold? So we don't know this. But as a theoretical exercise, if this inequality holds, then you can show that this convergence happens exponentially fast. With basically there is no additional error term. Okay, because now you're kind of restricting the class of measures which satisfy that inequality. Okay, so to summarize, for the so what we have done is there is this popular SVGD method, which in some sense is a regularization of the Wasserstein flow, but you can deregularize that flow and get a deterministic approximation to the Wasserstein flow, okay, to the Langevin dynamics. And the flow that we proposed, actually it interpolates between the Langevin dynamics and SVGD dynamics. If I choose the regulation parameter to be 1, I get SVGD. If I make it closer and closer to 0, you basically get the Langevin dynamics. Okay, so that is related to the sampling. But in the case of generative modeling, we will see that nicely this idea of again the regularization comes into picture, which is again, let's go back to this example of GANs, where so I'm looking at, so I have a family of discriminators and this is my family of generators. And one of the popular family of discriminators that is chosen is an RKHS ball. Okay, so people familiar with the MMD GAN, this is precisely like you choose your function class to be an RKHS ball. Okay, so so the MMD between two measures is nothing but choose this ball to be an RKHS ball, and then this refers to what Rahul was telling about. You take these measures, you put them in the RKHS and look at the distance between these functions, embedded functions in the RKHS. So I'm just looking at the mean of these functions with respect to the kernel, and then you look at the distance between those means. Okay, that is called as MMD. And there was this work where you use MMD as a cost function and 2 Wasserstein as the geometry. Okay, so when you do this, so remember in the case of sampling, we use KL as the energy function and 2 Wasserstein as the geometry. If I use MMD as the energy and 2 Wasserstein as the geometry, then you get a corresponding gradient flow. So this is the Wasserstein gradient flow of MMD square. Okay, but this paper actually calls it as like the MMD flow. Okay, so MMD flow means we may be thinking it is actually the flow with respect to the MMD geometry, but it is actually the flow with respect to Wasserstein of MMD. Okay, so we get a flow like this, and this can be perfectly discretized. And this is the particle discretization of that. And as you see, in this case, there is no appearance of the target measure pi. This only depends on, I give you initial samples from a target measure, and I want to generate new set of samples which look like as if they are coming from the target. Okay, so you have a particle discretization of this PDE, but the problem is when you look at the time discretization of that PDE as the time parameter k, as it basically goes to infinity, the MMD between your iterates to the target, they don't go to 0. Okay, and that is because this MMD functional is not convex with respect to the Wasserstein geometry. So there is no hope that you would expect that this convergence happens. You basically just go and hit some barrier term. So you basically don't really converge to the target pi. Okay, so as you can see, like there is a toy simulation here. So the blue circles that you see are the target distribution. Combinedly is the target distribution. Okay, and now we have these particles. So I basically start with a collection of particles and then evolve these particles associated according to this algorithm. And you see, as the iteration grows, you don't have a perfect convergence to the target. Okay, and that is because this MMD cost is non-convex with respect to Wasserstein. And what we consider here is a Wasserstein gradient flow of deregularized MMD. Okay, so now, so this is done jointly with a bunch of people. Okay, so the idea of deregularized MMD. Okay, so if you take MMD, I already mentioned that MMD is nothing but the distance between the means computed with respect to the kernel for these measures. Okay, a simple calculation will show that this is nothing but you look at the likelihood ratio d mu by d pi is your target. This likelihood ratio is smoothened through the integral operator. Okay, by smoothing the likelihood ratio through the integral operator is precisely MMD. Okay, now carry on the intuition that we had before. I can deregularize this object by looking at this object, so that as lambda goes to 0, this entire thing is an approximation to the identity operator. So as lambda goes to 0, you can show that this quantity actually approaches to chi-square. So which means, suppose let's say your energy is chi-square and my geometry is Wasserstein. This gives you a class of PDEs called the porous medium equations, which are very, very popular in the applied mathematics community. And how do you discretize this porous medium equation is also a question. So people use use like type of a KDE type of estimators to approximate these PDEs. So here what we are proposing is you can use a regularization type of an idea to approximate these PDEs. Okay. So in fact, chi-square is strongly convex with respect to W2. So which means if I'm actually solving a Wasserstein flow of chi-square, you will converge to the target measure pi. Okay. So now given that chi-square is approximated by DMMD, so the hope is that as I work with smaller and smaller regularization parameters, you can actually converge to the target. Okay. So that is a problem with MMD because MMD basically smooths the likelihood ratio, but you can de-smooth the likelihood ratio and you can still converge to the target. Okay, so again, you have a similar type of a result. Okay, so here you need like more nasty conditions. Okay, so you need like some smoothness of the likelihood ratio at every iteration. Under these assumptions, you can show that you have an exponential convergence to the target plus an additional error term, which depends on the regularization parameter lambda. Okay, as your lambda goes to 0, you can kill off the remainder term and you have an exponential convergence to the target. Okay, I think in the interest of time. So you also have a particle version, and in the particle version, you can show that this empirical measure that you get, it basically also converges in KL to the target distribution with an exponential convergence plus, so you need to choose the step size appropriately. So the step size appears both in the approximation error and also in the discretization error. And if we choose the step size appropriately, then we can have exponential convergence to the target. Okay. And the algorithm is very simple, very similar to the MMD flow. It's just that you have an additional factor of you need to compute the covariance operator, and this entire thing can be implemented using kernel matrices. Again, the order of computation is going to be cubic, unlike in the case of MMD, but you have a convergence to the guaranteed convergence to the target in this case. Okay, so here are again toy simulations. So this is related to the Wasserstein flow of MMD. This is the Wasserstein flow of DMMD. As you can see, the DMMD one actually converges to the target compared to the MMD. Okay, and this is the behavior of what happens with the regularization parameter. As a regularization parameter, if the regularization parameter becomes too small too quickly, then you have a problem with the convergence. So if the regularization parameter is also too large, then there is a large approximation error. So therefore, the regularization parameter in some sense lambda has to basically decay at a certain, I think this is something that you need to tune in your algorithm. So you need to choose lambda appropriately so that the algorithm kind of nicely converges, gives the particles which appear to have been drawn from the target measure pi. Okay, so I have presented this idea of deregularization, which can be used in deregularizing either the geometry or the energy functional, and these have applications in sampling and generative modeling. Okay. Thank you, and I can take any questions.